Welcome, my dear students. Let me give the hands-on demonstration of BCD and arithmetic, ASCII arithmetic instruction. Open the DOS box. Then at the DOS prompt, create the file using the DOS editor, edit. Say the file name demo1.asm, say. You already know the structure of the assembly language program. The different section of the assembly language program are: the first is the title directive, where you can write the title of your program. So title directive, DA instruction demonstration. Then the next section is dot model small. Dot model is a assembler directive and small is a memory model, okay, which defines the memory model for that can be used in your program. And then dot data, which is optional. Here it is not there, which reserves memory space for constants and variables. Then we have dot stack, which is optional. We are not used here, which reserves memory space for storing data in the stack. And then the next section is the dot code, which is an assembler directive, which reserves memory space for program instructions. Then what follows is the program instructions, okay. And then when you reach the end of the program, we use the end assembler directive to end the program. Okay. So after the dot code, we are initializing the data segment using these two instructions: move x, data, move ds, ax. Okay, these are the two instructions used to initialize the data segment. So now to demonstrate DA instruction, you already know DAA instruction is used after the add instruction that adds two packed BCD numbers and to get the result in a packed BCD form. Okay. So DA instruction is used after add instruction. So to load the BCD 53H into AL register using move instruction, move AL, 53, which is the first BCD number, into AL register. So since DAA instruction works only on AL register, so move any one of the packed BCD number into AL register. Okay. Next, load the second BCD number 29 into CL register using move CL, 29. So the first BCD number is in AL and the second BCD number is in AL. Then add the two packed BCD number using add instruction, add AL, CL. Note that the result of addition should be in AL register, okay, because the DA instruction works only on AL. So it converts the content of AL register into packed BCD form. Okay. And then after the add instruction, execute DAA to convert the result in AL into packed BCD form. then move h comma force h in 20 minutes. These two instructions will bring us back to the DOS prompt. Okay, then end the program using end directive. Let us save the program. That's it. Then the next step is assembling the program using MASM assembler. Issue the command MASM demo1 dot asm and semicolon at the end. So this command will create .obj file. Then link the .obj file using the linker. The command is link demo1 dot or demo1 simply, and then semicolon. So this command will create the .exe file. Then your program is ready to run. So use the debugger to debug the program. So I am using the AF debug to debug the program. AF debug, the command is AF debug followed by demo1. Now your program is loaded in the program window, and just we will single step the program. We will debug the program in single step. For single stepping, just go on pressing the F1 key. See, the first instruction is executed. So these first two instructions will initialize the data segment. I'll leave it and come to the third instruction, move AL comma 53. 53 is loaded into AL register. Observe the at the top in the register window, observe the AL content. It is 53. AX is divided into AH AL. So in AL we have the packed BCD number 53. Then execute this instruction. Now the second packed BCD number is in CL register, that is 29. Then execute the add instruction. Observe the result in AL now. See, now the AL register contain the hexadecimal value 7C, which is not the correct BCD number. So we have to adjust the content of AL register into correct BCD number. So addition of 53 and 29 should yield 82. That is what the DA instruction does. So 7C is not the correct BCD form. So the correct BCD form is 82. So execute DA instruction. You know how a DA instruction works. You see, observe the AL content now. In AL, the result is 82. That is correct BCD form. Then quit the debugger. Next, demonstration of DA instruction. Next, the demonstration of DAS instruction. You can create a new file. Edit demo2.asm. Title. DAS instruction demonstration. Dot model small. Dot code. Initialize the data segment. Move AS comma. Rate data. Move yes comma AX. So how this DAS instruction works? So this instruction is used to convert the result of subtraction of two backed BCD numbers to a valid BCD number. So this instruction is used after the sub instruction that subtracts the two backed BCD numbers to get the result in a valid BCD format. Load the first BCD number, move AL comma into AL only, 32H. Load the CL register, the second BCD number, then subtract CL from AL. So after subtraction, the result will not be in correct packed BCD form. So to obtain the result in AL with the correct BCD number, you execute DAS instruction, DAS. So this DAS instruction works on AL register. Okay. So the content of AL is converted into the valid BCD number. Then move AH comma 4CH 21H. Then end it. Now let us execute this program. Assemble the program. Masm demo2 dot asm link demo2. Then debug the program using AF debugger. AF debug demo2. Now debug the program in single step by pressing F1 key. Yeah. Execute move L comma 32. So first number will be moved into L register. So observe the L content, it is 32. Then the second BCD number 17 is moved into CL. Observe the CL content, 17 is moved to CL. Then subtract. See, after subtraction, result would be in AL, which is 1B. Okay, which is not the correct BCD number. So in order to adjust the content of AL into correct BCD number, we'll execute DA instruction. Sorry, DAS instruction. Now execute DAS instruction. See, yeah, the correct BCD number is 15. Okay, observe the content of AL. It is 15. Okay, so subtracting 17 BCD from 32 is 15 BCD, isn't it? Yeah. Then demonstration of ASCII arithmetic instruction. Edit demo3.asm. Title directory is optional. You can either write or you can just ignore. Title is AAA instruction demonstration. Dot model small and dot code. Move x comma at the rate data. Move ds comma ax. Now, what is the purpose of AA instruction? The AA instruction can be used after addition to get the correct result in unpacked BCD form. So this instruction is used after addition that adds the two ASCII codes for the decimal digits to get the correct result in unpacked BCD form. So load the first ASCII code into a register, move AL comma 34H. This is the ASCII of the number 4. Okay. And the second ASCII code, move CL comma 38H, which is the ASCII of 8. So 4 and 8 are the unpacked BCD numbers whose ASCII equivalents are 34 and 38. Next, add these two. While adding, you have to store the result in AL. So execute add AL comma CL because AA instruction works only on AL register. After addition, result in AL will not be in unpacked BCD form. So you have to ASCII adjust after addition. You have to execute AA instruction. So what is the addition of the unpacked BCD number 4 and 8? So 4 plus 8 is 12. In unpacked form it is 0, 1, 0, 2. Okay. So in AH you should have 0, 1 and in AL you should have 0, 2. Save the program. Assemble the program, MASM demo 3.asm. Link the program. So in demo 3, then AF debug, demo 3. So the program is loaded in the program window. Then debug the program in single step, press F1 key. So the first unpacked BCD number 4, whose ASCII is 34, is loaded into AL. If you observe the AL content, then the second ASCII code 38, which is ASCII equivalent of the BCD number 8, is loaded into CL. So you observe the content of CL 38. Then add AL comma CL. If you add, so what is the result? 6C, which is not the correct unpacked BCD form. So in order to get the result in unpacked BCD form, execute AAA instruction. Then observe the result in AX. AH contains AL contain 12 and sorry, AL contains 02, AH contain, it should be 01. Then demonstration of AAD instruction. Demo 4.asm. Write the title AAD instruction demonstration. Small. Dot code. Move x comma at the rate data. Move ds comma x. So what is AA instruction? AAD instruction. So this instruction add AAD. This instruction AAD can be used to convert the two unpacked BCD digit in AH and AL register to the equivalent binary number in the register AL. So two unpacked BCD digit in AX is adjusted to the equivalent binary number in the register AL. And note that this AAD instruction should be issued or executed before the division instruction. First load AX register with two unpacked BCD number. Move L comma 0 7H. Move AH comma 02H. These are two unpacked BCD form that will convert into equivalent binary number. Execute AAD instruction. So this AAD instruction will convert the two unpacked BCD digit in AH and AL into equivalent binary number. Save the program. Sum of the program. Demo 4.asm. Link. Demo 4 and AF debug. Demo 4. Go on single stepping. First unpacked BCD number is moved into AL, which is 07. Second unpacked BCD number 2 is moved into AH. Now AX contains 02, 07. So these two unpacked BCD number is converted into equivalent binary number, okay, using AAD. See, after execution of AAD, in AL we have 1B, which is the equivalent binary number. Then demonstration of AAM instruction. Create another file, demo5.asm, title AAM instruction demonstration. Dot model small. Dot code. Move AX comma at the rate data. Move DS AX. Then what is AAM instruction? ASCII adjust after multiplication. So the instruction AAM can be used to convert the result of multiplication of two valid unpacked BCD number in AX. Okay. So this instruction is used after multiplication, okay, that multiplies two valid unpacked BCD number to get the correct result in unpacked BCD number. Get the first unpacked BCD number into AL. Move AL comma say 04H. Move the second BCD number into CL, say 06H. Now execute the mul instruction, mul CL. So mul instruction will multiply the content of L and CL and store the result in AL. AX. So now, right now, after the execution of mul CL, okay, result in AX will not be in unpacked BCD form. Okay. So now to get the result in AL to correct unpacked BCD form, execute ASCII adjust after multiplication instruction. AAM. Move H, 4CH. So what is the result of multiplying these two unpacked BCD number? 4 into 6. So result will be 24. Okay, in unpacked BCD form it is 02, 04. In AX. Some of the program MASM demo 5.asm link demo 5 AF debug demo 5. Now single stepping. See, first unpacked BCD number is loaded into AL, so 04. Second unpacked BCD number loaded into CL. So observe the CL content 6. Then multiply AL CL. Result will be in AL C 18. 18 hexadecimal it is. Okay. So which is not the correct unpacked BCD form. Okay. So execute AAM instruction. After executing AAM instruction, observe the AX content. You see 02, 04. Okay. So result of multiplication of 4 and 6, which is 24, 02, 04 in unpacked BCD form. Next demonstration of AAS instruction. Create another file. Edit demo6.asm. Title AAS instruction demonstration. Dot model small dot code. Initialize the data segment. Okay, so what this AAS instruction does, the AAS instruction can be used after subtraction, this sub instruction, to get the correct result in unpacked BCD form. Okay, so this instruction is used after sub instruction that subtract the two unpacked BCD number to get the result in unpacked BCD form. Get the first unpacked BCD form, unpacked BCD number into AR, move AL comma 38H. So 38H is the ASCII equivalent of the unpacked number 8. So move the second ASCII code for move CL comma 32H, which is the ASCII equivalent of the unpacked BCD number 2. In other sense, we are multiplying the two unpacked BCD number. Sorry, we are subtracting the two unpacked BCD numbers. 2 is subtracted from 8, so the result should be 6. Sub L. So after subtraction, the result in AL will not be in correct unpacked BCD form. So to get the result in unpacked BCD form, execute AAS instruction ASCII adjust after subtraction. Save the program. And demo 6.asm. Then the link demo 6 and AF debug demo 6. So single step. See the first ASCII code for the decimal 8 is moved into AL, which is 38. AL contains 38. Observe the register window. AL contains 38. Then CL contains 32. Subtract CL from AL. See result. Observe the AL content. It is 06. Okay. Subtracting 2 from 8 is 6. Okay. Yes. Hope you understood.